My name is Zach Shwerakonti, and I'm a research associate at the Alan Turing Institute in London. And I would also like to introduce my colleagues and co-organizers of the seminar series, Andrea Pizzaferato, who is an assistant professor at the University of Bath, and Temis Botsas, who is also a research associate at the Alan Turing Institute. And for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. So for the benefit of those joining us for the first time, I would first of all thank you and welcome you, and also like to briefly introduce the topic of this bi-monthly series, that is physics-enhanced machine learning for engineering applications. So physics-enhanced machine learning is an upcoming subfield in machine learning and deep learning that aims to integrate known physical understanding of observed phenomenon into the machine learning framework. Advantages include data efficiency, interpretability of the prediction model, which are vital criteria for real-world engineering applications. And on a side note, if you are interested to share your work in any of our upcoming seminars, please feel free to get in touch with us. And as for the format of the seminar, our speaker will speak for 30 to 40 minutes, followed by a Q&A session. Questions may be asked in person or by using the raise hand function, or by simply typing the question in the Zoom chat. So without further ado, I'll ask my colleague Temis to introduce our speaker for today. And with that, I thank you all.
Thank you very much, Zach. Thank you all for coming. We are very delighted. Today's speaker is Dr. Fehmi Cirak. He has a long history of research in computational mechanics. He started with a PhD in computational structural mechanics from the University of Stuttgart. He continued with being a postdoctoral fellow in aeronautics at the California Institute of Technology. He was also a senior scientist at the same place in the Center for Advanced Computing Research. And he's currently a reader doing both research and teaching on computational structural mechanics in Cambridge University. Finally, he's also one of the organizers of Turing's Digital Twins for Infrastructure and Construction program. And with that, we're ready for you, Dr. Cirak. Whenever you're ready, go ahead.
Thank you for the introduction. I would like today to introduce our work on statistical finite elements for digital twinning of self-sensing structures. This is a joint work with Eki Fepriando, who is a postdoc at Turing, and Liam Butler, who was a postdoc at Turing some time ago. And he is currently assistant professor at the University of York in Canada, and with Mark Girolami, whom probably all of you know already. As we know, today most engineering structures are designed using finite element models, and these models are inherently misspecified because of lack of operational data during design and innate uncertainties like variations in material, loading, geometry, and so on. These uncertainties are currently considered through codified safety factors, and as you can imagine, this leads to very inefficient structures. Fortunately, we have more and more data coming from engineering structures in operation. And in our context, this data is mostly strain data. And here I have included 3 examples. On the left, you can see how one can obtain strains on the surface using digital image correlation. Or in the middle, you can see how one can obtain strains along a line using a fiber optic sensor. So these are railway sleepers equipped with fiber optic sensors. On the right is a technique similar to digital image correlation. So using satellite data, one can reconstruct the strain distribution on a city level, for instance. And in this example, there is a tunnel which has been dug out here along this line, and you can see this led to some strain concentrations around that area. So if we can somehow make use of this data and integrate it with our finite element models, obviously we can make more accurate and reliable predictions and make more efficient designs, and later during operation of this structural assets make more rational decisions. So this is our objective. We would like to develop a statistical framework for synthesis of data and finite element models. This is our setup. So we have given a real system like a bridge, like shown here. Then we have a approximate finite element model of the bridge. Now we have coming more and more data coming from an operational bridge. And we would like now to combine this data into the finite element model and somehow make better predictions about the real system. There are several challenges here. First of all, the finite element models are misspecified due to various modeling assumptions and uncertainties mentioned on the previous slide. In addition to that, in an engineering context, the data is usually scarce in contrast to, say, machine learning context. So we decided to use a statistical framework in order to achieve this dimension goals. So specifically Bayesian modeling concept. So all the uncertainties in the data, model parameters, and the finite element model itself are considered as are represented as probabilities. So this means this results in a set of random variables with corresponding probability density functions. We have a finite element solution U, so we have a corresponding probability density function. We have data Y. Then we have associated with data probability density function PE, which indicates the measurement errors. So we want to combine this somehow in order to infer the probability density Z for a true system. So this is essentially our entire setup, and it illustrates also our broad approach. So during the presentation, I will talk about the details of this approach. So this is the outline of my presentation. I would like first to introduce our statistical data generating model. Since we are dealing with Bayesian statistics, so we have prior probability densities associated with finite element solution and with a model misspecification errors. We will combine these prior probability densities and the likelihood function which encodes the data generating model and infer some posterior probability densities. So we use for that Bayesian inference, and then we have some hyperparameters which we will also learn. I will show two examples. The first example is a verification example, a one-dimensional verification example, just to check that everything is okay. The second example is a validation example. So this is an operational railway bridge. Let's start with a data generating model. So our data vector Y, in our context, Y is usually restraints, is decomposed into three components: a finite element component U, model discrepancy component D, and the error component E. In addition to that, we have the projection vector P, which essentially maps the finite element solution to a sensor space Y. And we have also here a parameter rho, which is a scalar parameter, which we will later determine. So all the components, essentially U and D are random vectors here. And in addition to that, if we add this first two components, this is equal to a true system or true structural response set. So we are assuming that each of these random vectors, U, D, and E, are normally distributed. And this is not necessary in order to make a subsequent computations simpler. Since these are normally distributed, so we have a corresponding mean, indicated always with bar, like U bar, and the corresponding covariance matrix, like C, always indicated with C here, and with some subscript U, D, and E. So the measurement noise E is usually known because this is a kind of a property of a measuring equipment we are using. But we have to now specify U and the finite solution U and the model specification D. Let's start with a finite element solution. In order to make things more concrete, so I have included here a very simple PDE, partial differential equations. This is a Poisson-Dirichlet problem. So, I mean, this essentially could be is the heat equation, right? So U is here the temperature, F is some source term, and kappa is the diffusion constant. So we would like essentially by solving this problem on a domain, would like to know the temperature U over the domain. So we here in our context the forcing is random at F. It's random, and the diffusivity is a random kappa. So in both, we assume again that they are Gaussians to simplify things. So we discretize these equations using finite elements. I hope you are familiar with finite elements. Essentially, what we are doing is we have here three different fields, U, F, and kappa. And we discretize them or approximate them using with some shape functions, basis functions. And for the displacement and forcing, we use usually the same basis functions phi. And for the kappa, the diffusivity, we use a different basis function psi. If we plug in these equations into a weak form of this our PDE, so we obtain as usual finite element equations, which are probably familiar all, so which looks like something like this. So A is in a structural context called stiffness matrix, and I think here in heat they call it conductivity matrix, but it doesn't matter. So it's always the same matrix. And now U and F are, of course, now vectors, and kappa is a vector as well. Here, the stiffness matrix obviously depends on the diffusivity kappa. And since we assumed the F and kappa are Gaussian, so we essentially the discretized or the coefficients kappa, the coefficient vectors kappa and F are multivariate normal vectors with corresponding mean and covariance. So then we can, I mean, formally write the random solution, which looks like this. So by just inverting this equilibrium equations, we obtain a random solution, which of course depends on, it has to be random because F is random, so U has to be random. In one more difficulty is here is because we are inverting the stiffness matrix. So the solution depends non-linearly on this diffusion vector. So this means U is not a Gaussian anymore. Although kappa and F are Gaussians. So we want to make things, the subsequent computation simpler. So we want to approximate that again as a Gaussian. So what we can do is we can determine its mean and covariance and just postulate a Gaussian. So in order to do that, so we have to solve this previous equation. So we could use any of the conventional approaches like Monte Carlo, perturbation, polynomial chaos expansion, and so on. But we decided essentially to use a simple perturbation approach. So this is our solution, U, which depends on the random vectors kappa and F. So we just develop it in the Taylor series and keep only the linear terms. And from that, for this essentially this on a Taylor series with only the constant and linear term, we can compute a mean, which looks like this. So this is a standard finite element solution. So here we have a mean of a diffusivity, and mean of a forcing vector gives us a mean solution. Then we can compute also a covariance matrix, which looks something like this. But I mean, this looks slightly complicated, but if you look at a little bit in more detail, it's straightforward. So we have here CF, this covariance of forcing prescribed. C kappa, again, prescribed covariance of diffusivity. And in addition to that, we have the stiffness matrix evaluated at kappa, at a mean of a kappa. And a slightly unusual term is essentially this derivative of a stiffness matrix with respect to a kappas. So in any case, I mean, one can implement, write these equations down and then implement it once, so then one doesn't have to see this equation anymore. So this is our knowing the mean and the covariance, so we can write down our approximate finite element density. It's a multinormal distribution, which looks like this. So to make things concrete, let's look at a simple example. This is a 1D equation. So kappa is a 1 and F is random. And it has a mean of 1 and a standard deviation of 0.1. Here on the left, you can see the forcing, the random forcing over a domain from 0 to 1. So these are different, I think 5 or 6 different samples from that multinormal distribution. And this blue area is the 95.5% confidence region, which is like 4 times the sigma f, the standard deviation. So we can now plugging in this random forcing into the equations on the previous slide. So we can compute a random solution, which looks like here. So again, here I've plotted, I think, 5 different samples. And then you can see the 95% confidence region, which we obtained using the equation from the previous page. So we have now the prior for our finite element solution. So we need also prior for a misspecification error, D. Obviously, we don't know much about the misspecification, so we have to kind of assume a relatively weak prior. And I mean, if you are of a more engineering background, essentially the reasons for this model misspecification errors is if you model your bridge, for example, you make certain assumptions about the boundary conditions, about geometric dimensions, and so on. So this model misspecification error is intended to take care of all of those errors. So in any case, so we are assuming essentially for this misspecification error D, again, a normal distribution, and with a covariance kernel here, like with a squared exponential kernel shown here. Sigma D is a standard deviation, and then we have some length scale LD. And I mean, this specific kernel has 2 hyperparameters in sigma D and the LT. And so we can now compute from this kernel by plugging in our sensor positions, the covariance matrix CD. So then we have our normal distribution for the discrepancy, which depends on this hyperparameter sigma D and LD, obviously. There are other kernels. You don't have to use this kernel. You get like a modern polynomial periodic and so on. So we could use any of those kernels, or we could use any combinations, multiplicative or additive combination of those kernels. So this is a summary so far. So we didn't see any data yet. This is, as mentioned, we decomposed our observations in 3 components: a finite element component, a discrepancy component, and the error component. And this is kind of our graphical model. And importantly, we set all the priors, the random variables U, D, and E, before seeing the data, are normally distributed, and we have this structure shown here. We have in our model also 3 parameters, so the scaling parameter and the 2 covariance parameters, which belong to the squared exponential kernel. So now we will update these distributions in light of observation data using a bias formula. So this is a bias formula. We have on the right the prior shown on the previous page, which we derived for the finite element solution. Then we have data likelihood, which is results from our observation model. We obtain from that a posterior, like shown on the left. So at the bottom, we have the marginal likelihood, which kind of makes sure that we have that the left-hand side essentially, or that the right-hand side integrates to 1, so that we have a probability distribution. Since now we assumed that all our priors are Gaussians, we can now write all these quantities simply by inspection or by solving very small equations, or it's very straightforward to write down these the distributions shown here. So first for the data likelihood, so data, because of this structure is a normal distribution. So this encodes essentially our statistical model. And so next point is the posterior depends. So this is U conditioned on the observation data Y, but we have still here essentially the hyperparameters rho, sigma d, and LD, which we of course don't know. So we don't know them, but we are interested essentially in the density of a finite element solution conditioned on the observations. So the usual way in statistics is to marginalize out or to integrate out these hyperparameters using formula, doing it formula like shown here. And in empirical bias, this is the approach which we are using. Essentially, this integral is evaluated using just one quadrature point. So essentially evaluating this integral at this quadrature points with rho star, sigma star, and L star. Okay, so I will later get back to that, how we determine this quadrature points. So after we plug in into our marginal likelihood, then we have posterior, which we can use. So before determining this quadrature point, so let's first determine the posterior, U conditioned on Y. So everything is Gaussians. So hence the finite element posterior must be Gaussian as well. Then we can, by just inspection of our data generating model and the different distributions, we can write this joint density for U and Y, which has to look like this. Then we can compute the essentially U conditioned on Y using standard Gaussian relations, which you can look up in any textbook on statistics. So the posterior mean looks like this. So if we look at this a little bit carefully, so the posterior U conditioned on Y looks like it depends on the mean of a prior and the difference between the measurement and the prior mean. Okay, so essentially. And then we have here some factors, and these factors depend all on the covariance matrices. So, and the covariance matrices express our essentially trust, or how much our confidence in the different components. Okay, so if we trust the finite element solution more, the posterior would be equal to a prior finite element mean, or if we trust the measurement more, this equation would give us essentially would be equal to Y. And then the next we have this posterior covariance, which looks like this. So this does not depend on the data. I mean, there is nowhere Y. So we can see here we have a prior covariance. So essentially we are always subtracting something from this. So and doing any sorts of measurements increases our confidence in the solution in the posterior. So, but how much we subtract from that, it depends essentially in the ratio of different covariance matrices, CU, CD, and CE. So this is just some intuition how our posterior looks like. We have still in the posterior hyperparameters, rho, sigma d, and LD. And in order to determine that, so we look at the marginal likelihood. And this was the denominator in the bias formula. So this, the marginal likelihood looks like this. So if we look at this, this says essentially this is a probability of y given rho, sigma d, and LD. So intuitively, it makes sense now to essentially choose these hyperparameters so that the observed, the probability of the observed y is maximum, right? So this means, so we maximize this marginal likelihood with respect to sigma and LD, and this gives us our star quantities. So this is where we will essentially do our one-point integration. Alternatively, we can also sample the marginal likelihood with MCMC, and then we could take the empirical mean as our start quantities. In our subsequent computations, so we use the second approach. So these two different approaches have their advantages and disadvantages. So I will not go into details here. Okay. So two examples. The first example is our verification example. Again, we look at the one-dimensional Dirichlet Poisson problem. Kappa is here 1, the diffusivity is 1, and the forcing is random. And this is a Gaussian process, which looks like this. So 1.97 is the mean, 0.3 is the standard deviation. Here, I've plotted the forcing over the domain, so 0 to 1. The blue line is the mean, 1.97, and this blue region is a 95% confidence region, about 4 times 0.3. And on the right, you can see the finite element solution in blue. So finite element mean and the corresponding confidence region. In addition to that, I have plotted here also in gray the assumed true system density. So this is the black one, is the one which we don't know. This is a true system density. And you can see here this has obviously more structure than a finite element solution. So we create synthetic observations by sampling from this black-gray distribution, or by the assumed exact solution. Here we use a variable number of observation locations, 4. So ny is the number of observation locations, 4, 11, and 33 locations. And we, in addition to that, at each location, we do multiple readings. This is NO from 1, 10, 100, or 1,000 readings at each of the positions. So the synthetic observations now we obtain from this assumed true density, and we have here, or in addition to that, also this error, the measurement error, 2.5 times 10 to the minus 5. So this is a measurement error. Okay. And
sorry, there is a question in the chat.
Yeah, I just see that. So,
okay.
Sorry.
That's okay.
15. This is a true system response, assumed true response. I mean, obviously, so this is a made-up example, right? And we are solving this problem, which has this blue solution. It is because F is random, so we have also this confidence region, this light blue area. And so we are assuming here that our true equation, which we don't know how it looks like and so on, is essentially gives this black solution. I hope this answers your question. Okay. If you have any other questions, please ask me. I mean, I don't know. I think we have quite mixed backgrounds, so let's go. Okay, so from this PZ, we sample synthetic observations, right? Different number of positions for 1133 and different number of readings at each position. So first, in our approach, the first task is always to determine the hyperparameters, so rho, sigma d, and LD, which belong to the covariance, to the mismatch, essentially. And so I have now I am assuming that you have only 11 sensor locations, and we have different number of readings, repeated readings, and we are obtaining this hyperparameters by sampling the marginal likelihood with MCMC. Okay, and so we have a histogram for rho, sigma d, and LD. And if we focus on one of them, let's say rho, so if you have one reading, this looks quite flat. The histogram which we or the probability density which we obtain looks quite flat, so it's not very informative. But if we do more and more readings, right, this gets spikier and spikier, right? So I mean, we can see here that the rho should be probably something like 0.77, right? So this shows us that this entire thing seems to be converging. So convergence means here that the mean is converging and the variance is decreasing. And we use this essentially the means, empirical means, which we obtain from these plots as our point estimates for these hyperparameters. So next we look at the posterior finite element density. First, we have in blue the prior finite element density. So I showed you this already before, right, in 2 slides before. So on each of these pictures, they are the same. This is a prior finite element solution. And in each of these plots, we have a different number of NY, number of positions, and number of readings. So here we have 4 locations and 1 reading at each. Here we have 33 locations and 100 readings at each. I mean, we have many more of these plots, but I am showing you a few of them. So if we look at the left top, so we have just 4 readings, and then you can see essentially that this inferred posterior element density in red, it lies somewhere in between a prior solution, prior density, and the observation points. Okay, this is in red. If we now use more locations and more readings, then you can see now that this is somehow converging towards the weakly true system response, that's the black curve which we had, right? So this is a good thing. We can look also the inferred true solution, so Z conditioned on Y. Again, in blue, the prior finite element density is the same on 4 plots. And if we look here, for example, top left again, so we have 4 readings, and you can see essentially, I mean, the inferred true solution is not very informative. I mean, the mean looks good, but the variance is quite large, right? But if we now keep using more locations and reading more and making more and more readings, so each of these points is a reading. So you can see that this is a kind of, again, converging to a weakly shape, and also the covariance is quite similar to the original covariance or I mean, obviously we are looking at variance. So the variance here is similar to a variance of a assumed true solution. So this is again a good thing. So next, I want to now discuss a larger example, so validation example. So this is an operational railway bridge, which is somewhere along the UK West Coast Mainline, I don't know, Shropshire or something like that. So it's a steel bridge, and this is a side view of a bridge. So this is a one train line, and this is a second train line which is crossing it. So we are concerned about this bridge. Okay. So this is the structural layout of a bridge. It consists out of 2 longitudinal I-beams and 21 transverse I-beams in between. And on top of that is a concrete deck. This is a relatively small bridge. I mean, it's not 7 meters, which is relatively short. And this bridge has been instrumented with a fiber optics monitoring system for measuring strengths by Liam Butler and his colleagues at the Center for Smart Infrastructure in Cambridge. So this is 2 more pictures from the sensor installation. So this is the main I-beam, right? And these are the transverse I-beams which are connecting here. And this is you see here these cables which we are attaching. So these are fiber optic sensors. So these are lines, and we can measure, make measurements along that fiber optic line. We model here just a superstructure. This is our finite element model. And I mean, you can, of course, it's an engineering decision how you want to model this. So we decided to use model it using shell elements. And so these are essentially, you can think also plate elements, which are rigidly connected at this, for example, at this T junctions and so on. So this is a relatively short, coarse mesh with around 4,600 elements. And we model the train essentially loading as point loads. So you can see here, I mean, 4 wheels or 2 axles of a train here, and then the others here. And inertia effects are neglected, so we don't do dynamics because, I mean, you can justify this because the bridge is relatively short. So this is
I believe, Dr. Cirak?
It looks like we
Yes, it looks like we've lost him. We get him back.
He is aware. He is aware. No, he's.
Okay. Apologies to everyone while we get him back. Let's see.
This won't happen when we're back to Turing.
I just realized my microphone was off. Apologies to everyone. We're trying to get Dr. Cirak back. I wish I had like some waiting room music to play right now. Maybe some lift lobby music. Yes, the seminars are being recorded. We're still ironing out some logistics to allow them to be put in public, but I will definitely let you all know. Okay. Welcome back, Dr. Cirak.
So I think the setup is okay, right?
Yes, yes, it looks fine.
Okay, sorry about this. I don't know what happened. I have to share again.
Yes, please.
Let's try again. Share. So you can see?
Yes, perfect.
Okay. So we were talking about this bridge. Sorry about the interruption. So we are comparing here the finite element and the measured strains. So this is this picture shows where our sensors are placed. So we are looking at the strains. So this is the east main I-beam, and we are now looking at the strains here at the center of the I-beam at the position 11. And we are plotting them over the strain over time. And the tool at the top, we have essentially the upper flange strain, which is measured here. And at the bottom, we have a lower flange strain, which is measured here. So these are the blue points are the measured strains, and the red line is a finite element strain. I mean, in this case, the agreement is quite well, but it depends on the train and so on. Yeah. Sometimes the difference can be significant. So, I mean, this is a standard finite element, so we didn't do anything statistical yet. And we will be now looking at the strains at the time instance 1, 2, and 3 along this east main iron beam, along this beam. So this is now the strains along that I-beam. So this is we have 40 sensors, 20 at the top and 20 at the bottom flange, right? And we have around 500 readings. And so if we now look at this carefully, maybe the left one. So in blue is in blue at the top and the red at the bottom. These are prior finite element strains before doing any readings, and with a respective 95% confidence regions. Then we have this dots are the readings, and after the readings, we in black you can see essentially the true flange strains, or upper flange and the lower flange. And I mean, similar things. These are similar plots, but at different times, at 2 seconds and 3 seconds. So we can see from here. I mean, if after we do a reading, this essentially this the 95% confidence regions become smaller in comparison to a prior. In addition to that, we can see that the mean of the inferred mean, the black one, so lies somewhere in between the sensor readings and the prior strains. So this looks everything good. And then next, we wanted to study essentially how about if instead of using 40 measurements, we use less measurements. Although we have 40, we want to use just 10, and just to see does using less measurements give us similar results, essentially kind of study the convergence of this thing. So on the top, these are the same plots like on the previous page. I just copied them for comparison purposes. And here at the bottom, these are essentially new plots. So you can see here that there are fewer dots, so they are fewer readings. So we have only 10 readings here. And you can, if you compare this, the black lines in the bottom with 10 measurements and the 40 measurements, you can see that the agreement is quite good. So having only a few sensors, we can get already quite a good idea about the trains in our system. So brief summary and conclusion. Essentially, we developed a technique, we call it statistical finite elements, which enables to synthesize observations and simulation data in a coherent or consistent way. We consider uncertainties in all the parameters as well as model specifications, so any modeling errors. As you saw in these examples, the inferred densities converge to the true densities. And as you saw in the last example, we can make already with limited amount of data estimates about the true densities. So this is important for real structures. So if you want to use this approach, for example, to create a digital twin of a bridge like a bridge which I showed you. And the additional benefit of this approach is essentially more or less we use standard finite element models. So this the model which we used for a bridge is a standard finite element model. We can use those models in order to create digital twins by just adding this statistical framework, building them statistical framework around it. And since this is a Bayesian approach, I mean, there are, of course, several extensions possible. We are currently working on those. I mean, one of them is essentially you can use the, we can do make model selection and model comparison in a consistent way. So most of the slides and the plots and so on, which I presented, you can find in these two papers. If you have any comments or questions, I'm happy to answer now. But please feel free also to write me an email, and I'm happy always to discuss.
Thank you so much, Dr. Cirak. And as you very well, thank you for your very insightful presentation. I will now open the virtual floor to questions. We have a question from Peter. Yes.
Hello. Thank you very much for the talk. I wanted to confirm one thing about this. So as far as I understand, this inference model would have a natural bottleneck, which is the prior for your inference. And I wanted to confirm that I understood correctly. The clever thing that you used here is basically in order to avoid solving the full forward map, which would give you the functional prior for the inference, you linearize your equation around the solution, and then it becomes just a matrix vector product instead of solving the prior, instead of solving the forward map. Am I right in this? And what is the limitation of this approach? And what are other things that people do to get functional priors in such inference problems with PDEs?
I mean, you are absolutely correct, of course. Yes, I mean, essentially, if we don't approximate the prior as a Gaussian, right, then the entire framework we cannot write a posterior down like a Gaussian, right? So we would have to do integrate. We have to do MC something for the posterior and so on, right? So this makes it quite complicated. I mean, our motivation was we are coming more from an engineering viewpoint. So our motivation was since the finite element is anyhow a prior, right? And so we thought essentially it doesn't make sense to spend a lot of effort in order to get its true density. And the other thing, I think, if you think more mathematical, right? Essentially, if you want to solve a forward problem, I mean, if you have to do some approximation because you get very high dimensional problems.
Mm-hmm.
So I think even the other techniques, like if you do like polynomial chaos and this and that, right, which can give you the beta priors or non-Gaussian priors, right? They don't scale really. I think there are no techniques essentially to solve very large forward problems.
And the problem is getting the prior, right?
Yes.
Thank you very much. Thank you.
Thank you very much for the question. We have another question from Paul.
Hello. I'm an engineer, so you have to keep the explanation simple. But at the end of the bridge example, you have your updated solution, which now shows that there's agreement between the real world and your improved model. But if you work back from that, can you say where the uncertainty or the mistake was, if you like, in the original model versus physical result? Is it in the loading, or is it in the model, the FE model itself?
Yes. I mean, this entire approach is quite flexible, but it comes with a cost, of course, everything, right? And you could, since we have this slide with the hyperparameters, you could consider those, you can have more hyperparameters. Your prior could have also hyperparameters, right? Which associated with, for example, I mean, if you say, for example, loading, right? So we could say essentially the standard deviation of a loading is a hyperparameter, right? And which we would propagate through a system, and which we could also infer. And it is possible. I mean, of course, I mean, since we are engineers, there is always, I mean, it involves always modeling, right? And at some level, and the engineer has to decide, right? If you cannot take everything what you don't know as hyperparameters, because then the problem becomes unsolvable. It becomes very large, right? So if you think that the loading is uncertain, we could try to infer that as well. Does it make sense?
Yes, it makes sense. But I guess the question is, what do you do next after you've reconciled your model to the measurements? Is the idea that you then update your FE model with a better knowledge of the as-built structure, and to enable you to make predictions with it of its future life or future behavior?
I think the way currently I presented it, it's not that useful for that purpose. I mean, it has to be, but there are ideas how to do that. It's more like I have a finite element model, and I have 5 measurements, right? So what do you do with that? I know, let's say you trust the finite, you trust your sensor measurements, but how about, you know, you measure the strengths here, and what are the strengths there, and so stuff, right? You could, in its current form, essentially, is more like that you can extrapolate your, what you call results over the entire bridge.
Oh, okay, I understand. Right. Yeah.
And if you want to apply to different problems, I mean, essentially, if you want to extrapolate, I think in machine learning people talk about extrapolation. So you want to apply to different loading or completely different setups, right? And then we have to change this, like it is more like an inverse problem. You know, we have to infer the material property and these and that. Right here, we said, oh, we don't. Let's say we don't want to know what it is actually.
Okay, thank you. I understand.
Thank you very much, Paul, for your question. If there's time, I have one question myself, if that's all right. I was wondering if we can take advantage of your calibration framework for use of lower fidelity, for calibration of lower fidelity finite element models. For example, when we have a situation where we need computational efficiency, whether we can use for example, lower resolution meshes, finite element meshes, and use our calibration framework using sensing data, whether this makes sense at all.
I mean, it makes sense. I just I wanted to share a screen, but I think it disappeared. You can one can extend. I mean, first of all, you can use a lower fidelity finite element model, right? And one can essentially. I mean, we don't really care from where your data, this sensor data comes, right? You could essentially use something similar. You use a low fidelity model for prior and a high fidelity model as measurements or better results, and you could update this prior. It's possible.
Right.
And one could also make a hierarchy of models. I mean, of course, it becomes everything more and more complicated. I don't know how much useful it is, but you could have several levels of models, essentially.
Right. Thank you.
Sure.
Are there any other questions? Does not seem so. All right. With that, we thank you very much, Dr. Cirak, for joining us today. And we hope that you can all join us on our next seminar, and we will inform you soon enough. Okay. So thank you all. Have a good day.
Bye-bye.
Bye.
Bye.